Hello everyone, welcome back to one more lecture of fundamentals of ecology. I will continue discussing how we model populations. In the previous lecture, we discussed the most simple scenario where populations increase geometrically or exponentially with time, and of course that is true under under the basic condition that the number of resources are not limiting for the population to grow, and of course that is going to be true only when the population size is small. As the population size get bigger, the resources do become limiting and the exponential growth gets cannot continue forever, right. And basically one of the fundamental questions in ecology of populations is what are the various factors that regulate the populations from going in the trajectory of exponential growth. Okay. So, today what we will do is we will look at how limiting resources, which could happen for a number of reasons, is can be modeled using mathematical equations, and how it produces some basic features of populations reaching a carrying capacity. Okay. And to do that we will use the continuous time framework. So, recall that in the previous discussion on population growth, we assumed that the populations were reproducing synchronously across generations. So, we could look at one time step as roughly equivalent to one generation, and we were looking at these discrete time steps over which the populations are changing. Now we will move to a continuous population dynamical regime, because in many organisms this discrete jumps may not be a realistic assumption. Okay. So, to do that, let us recall what we started off and wrote down as the equation for how populations change over time in the context of discrete populations, right. So, this was the equation we wrote. So, where lambda was 1 plus r tilde, where r tilde was basically birth rate minus death rate per generation, right. Okay. So, now ecologists are often interested in understanding how populations are changing at a given point in time. So, if I were to write down what was the change in population size at kth generation, I can write this as the population size at k plus 1th generation minus population size at the kth generation, right. Now, if I now substitute equation 1 in equation 2, I will get this to be is equal to lambda nk minus nk, and we know lambda is 1 plus r tilde. So, this becomes 1 plus r tilde nk minus nk, right. And then we quickly realize that the first term and the last term here cancels. Therefore, the change in population, okay, in one generation is basically given by r tilde, which is measure of per capita growth rate times the population size. Okay. And now what we can do is, inspired by this equation, the equation tells that the change in population size is proportional to the current population size, right. This is the basic interpretation of the above expression. So, up to this point we really have not changed anything from what we learned in the discrete time description of the populations. Now, the basic trick when we go to the continuous time description is to think of this one generation and make it more general. It could be any arbitrary discrete time step, and then we take this arbitrary discrete time step to be really small. In such a case, we can now the left hand side basically becomes change in the population size for an extremely small amount of time, and that actually is nothing but dn by dt. If we go back to a little bit of calculus that we have learned, it basically tells that what is the change in the population, change in population in an extremely small interval delta t divided by delta t, under the assumption that this delta t is really tiny. Okay. So, this is the interpretation of this expression dn by dt, rate of change of populations. Okay. So, now we know from the from this expression here that the rate of change of population is proportional to or the population size itself, and if we write down the proportionality constant as r, we now have basically a continuous time analog of density independent population growth. So, this equation basically captures density independent population growth in the continuous time description. Okay. Now, let us quickly again like in the discrete case make a couple of plots and see how we can describe the density independent growth in terms of graphs. If you were to write the population growth rate on the y axis, so dn by dt is the entire population growth rate. How does that change with n? That would be a straight line that passes through origin, okay, and with a slope of r. Okay. We can also write the same equation in the different way. If you were to choose the y axis as per capita growth rate. So, what is per capita growth rate? Per capita growth rate is growth rate. So, this is growth rate and this is divided by population size. So, this entire thing will be per capita growth rate, and if the per capita growth rate is a constant as a function of population size, that again is same as saying we have a density independent population growth, and basically the equation here and these two graphs, they are equivalent way of representing density independent population growth. Okay. Moving forward, this equation, let us understand this equation a bit better. So, these type of equations are called differential equations. Without going into mathematical details, let me describe two important properties. One is that if we know that n0 is the initial population size, then the population at time t would be given by n0 times e power rt. This expression is true whether r is positive or negative. In the case that r is positive, you will have an exponential growth like this. On the other hand, if the r is negative, this is for r greater than 0. On the other hand, if r is less than 0, basically the initial population declines exponentially like this, right. Okay. Let us now do one more simple calculation to familiarize and understand these concepts better, which is that of doubling time. Okay. So, what does doubling time mean? if we start with a population n0, how long does it take to get to n0? Of course, this makes sense only when the per capita growth rate is positive, then that is when the population increases. Let us say the time taken is capital T. Okay. So, if you were to now use this equation for this condition of doubling, so 2 of n0 will be is equal to n0 times this has happened over a time interval of capital T, right. So, what is capital T? How does capital D depend on the initial population size and the growth rate? So, let us see that. So, you can see that this initial population size just cancels on the both sides. So, you will have 2 is equal to e power r t. Let us take logarithm on both sides. So, we will have logarithm of 2 is equal to r times t, okay. And we are interested in finding out capital T, which is the doubling time, and then that would be nothing but logarithm of 2 divided by r. Okay. So, doubling time is nothing but logarithm of 2 divided by r. Okay. Recall that in the case of discrete generation model, right, t which we denoted by t2 was logarithm of 2 divided by logarithm of lambda, okay, where lambda was 1 plus r tilde. Okay. So, I would like you to think a bit more about how these two are different as a part of the assignment or an exercise, homework exercise. And you may recall that I had made a table how depending on the value of lambda you will get different doubling times. In the discrete case, I would encourage you to try the same thing for the continuous time using this formula. Okay. So, now so far what I have done is sort of a revision of how the density independent population growth looks like in the continuous time. Finally, we are all now set to study density dependent population growth. And this we will do in the continuous time domain. Okay. So, this we will do in the continuous time domain. So, what is the starting point for us? The starting point for us is to understand the per capita growth rate. So, what is per capita growth rate? It is the growth rate, population growth rate divided by the population size. Okay, this is the per capita growth rate. And if this was a constant, we had density independent population growth. So, what we now need to think of is how do we think the per capita growth rate will depend on population size when the population when there are limiting resources. Okay. So, I will draw this curve to indicate unlimited resources scenario or the density dependent independent scenario. Okay. Now, naturally we expect that when the number of individuals in a population increase, the amount of resources available for individual will decline. And a reasonable starting point is to assume that as a consequence the per capita growth rate reduces with population size n. So, okay. So, per capita growth rate can reduce with population size in many ways, in many different functional forms, right. Okay. So, what we will do is, for the sake of simplicity, we will assume that the decline in the per capita growth rate is a linear function of the population density. So, this is an assumption that we are making. Okay. When we assume, but let me just emphasize that all the other graphs, let me label them 1, 2, 3, all these 3 are what would one call negative density dependence, in the sense that the per capita growth rate is declining with the population size. All these 3 are valid density dependent population growths. Okay. However, for simplicity I am going to choose the line number 2 with this one, which is written in blue color, because it is a reasonable starting point and it is also mathematically convenient. Okay. And in fact, mathematical convenience is an important criteria when we choose to describe ecological populations in mathematical forms, because what is the point of a mathematical model that we can't even analyze mathematically. If I choose a really complex functional form and I do not know how to now analyze it, maybe it is not very useful anyway, right. Okay. So, what we will do is we will choose this, and in the one of the equations in the mathematics refresher class that I did actually showed what is the equation for this straight line that begins at r when population density is 0 and it hits k when population density it hits 0 when population density is k, is given by the equation for 2 is basically given by 1 minus n divided by k. To convince yourself this is fine, if you set capital N is equal to 0, right, when n is equal to 0, the per capita growth rate will be r, when n is equal to k, the per capita growth rate will be 0, and that makes sense. That is precisely what this linear equation does, right. Okay. So, what we can therefore now do is write the per capita growth rate to be equal to r times 1 minus n by k. Now, we can simplify this further by taking this capital N to right hand side. So, if I do that, so we have an expression for how population is changing as a function of time, and how it is changing as a function of time depends on the current population density in the following way, or n times 1 minus n divided by k. Okay. And now, what is k? You note that when n hits k, value of k, the per capita growth rate becomes 0. That means there is no growth in the population anymore. So, k is actually a crude representation of carrying capacity in the system. Okay. So, now what we have is a differential equation. Okay. Now, for many students in biology, oh gosh, this is an what do I do with this? It is hard enough to make plots. Now, you want me to solve a differential equation. Let me assure you that we can actually understand this equation without mathematically solving them by the means of graphs and by the means of intuition. We just have to think hard, think slowly, and we will be able to make good progress of what this equation is telling us. Okay. So, let us try to understand this. Before we do that, I want to introduce one important point here. So, the right hand side of the equation here, let me call this equation 3, because I think I have used the number 1 and 2 up to this point. Let me call this equation 4. First and foremost, equation 3 and 4 are basically mathematically equivalent. The only difference is that how it is, how the left hand side and right hand side are written. Okay. So, but mathematically they are the equivalent. we did plot the right hand side of the equation 3, that was a straight line that showed how the per capita growth rate changed with population size. Now what is this right hand side here? This right hand side, let us denote this by f of n, a function n, a function of n. This is basically the entire population growth rate dn by dt. dn by dt is the entire population growth rate. Okay. So now can we now plot this population growth rate as a function of the population size, that is Rn times 1 minus n by k. Again please go back to the math refresher video and check this. This function basically looks like this. It is 0 when population size is 0, okay, and it is 0 when the population size is 0, it is also 0 when the population size is k. Okay. So the population growth rate increases, reaches a maximum value and comes down to 0. So let us now try to understand how do we make sense of this, what is the use of this equation, how does it tell how population change over time and what value will the population reach if we wait long enough. Okay. So remember that at this stage from the density independent model we know that populations increase exponentially, right. Clearly that can't be the case here, right, because we have assumed that the per capita growth rate is declining with the population size. So to understand these type of differential equations we need to learn two concepts, very simple concepts. One is the concept of equilibrium. So the equilibrium is a constant when the rate of change is 0. So for our context the rate of change is in population size. So that means the dn by dt is equal to 0. So whenever whatever the population sizes at which the rate of change is 0, they would be called equilibrium population sizes. Okay. So that is one concept, the concept of equilibrium. The second concept is that of stability. Okay. So what is stability? The idea of stability is that let us say I am at some equilibrium, begin at an equilibrium. If you are at an equilibrium nothing will happen because the rate of change is 0, right, but then make a perturbation. What do I mean by a perturbation? Maybe add a few more individuals to the population or kills a few individuals from the population. Now ask, if you now let the growth and death happen, if the population returns to the equilibrium, we call such an equilibrium stable equilibrium. On the other hand, if the population moves away, from the equilibrium from which we made the perturbation, we call that an unstable equilibrium. Okay, so now let us try to apply the concept of equilibrium and stability to our equation, to our population dynamical equation given by this dn by dt is equal to Rn times 1 minus n by k. At this stage let me also say that this is called the logistic population model. Okay. I would like to caution a little bit, logistic population model also comes in the discrete time version. So and those are called logistic maps. but to avoid ambiguity, to make always remember that we are so far discussing continuous time logistic models. Okay. So, let us now apply the concepts of equilibrium and stability. So, let us find what are the equilibrium population values. So, how do we find them? We find basically we usually denote them by n star. Okay. So, all the population sizes for which dn by dt is equal to 0. How do I find dn by dt is equal to 0? I just set the right hand side, which I called f of n, right. I just set the right hand side to 0. So, that means r n star times 1 minus n star by k is equal to 0. Whenever this expression is true, we are at an equilibrium. So, now this is a multiplication of two terms. Multiplication of two terms can be 0 when one of the terms is 0. That means either this is 0 or this is 0. Okay. So, if the first term is 0, we will get the equilibrium 1, first equilibrium, which is basically n star is equal to 0. Of course, r is equal to 0 means the per capita growth rate is 0, and that is a really pathological case to consider. So, we will not worry about that. Okay. So, n star is equal to 0, and that means basically you are thinking of a locally extinct population or a population that basically does not exist in that area of your interest, right. The second equilibrium is 1 minus n star by k equal to 0. If you now rearrange the terms, this is basically same as saying n star is equal to k. That means there are two equilibria for this logistic population model. One is that of a local extinction, I say local because we are sort of thinking of studying population in an island where there is no immigration emigration, but there could be other areas where this species might be present. So, okay. Or an alternative is that of carrying capacity where n star is equal to 0, n star is equal to k, sorry. Okay. So, now we have identified the equilibrium population sizes. Okay. So, now what is the next step? We should now identify, are they stable equilibrium? Which of them, are both of them stable, one of them stable? Okay. Let us try to find that out. Stability. So, here is the trick to finding stability. There are actually two ways of doing it. One is a more mathematical way that requires you to calculate some derivatives. So, but I will not do that in this course. I will stick to a graphical way of identifying stable equilibrium. This is called the graphical analysis or a geometric way of thinking about population equilibrium. Okay. So, what I will do is I will plot the population growth rate as a function of n. You remember that this we already did this, it looks like this. We have a 0, there are two places where the population growth rate is 0, and in fact those are precisely the equilibrium values. So, what we start usually by doing is identify the equilibrium on this graph. Population growth rate as a function of n, there are two values at which the population growth rate is 0, and those are the equilibrium values. Okay. So, we first identify the equilibrium values, and having done that, this is 0, right. Having done that, we now ask which of them is stable, or both of them stable, or both of them unstable. Okay. Now, here is the interesting part. Remember what is stability. Stability basically is trying to tell us, if you make a perturbation, will the population stay there or does it move away. So, let us ask this question. Let us say there was an island with 0 population, and then I added a few I introduced a few individuals in this area. Okay. So, the question is it is sort of one sort of example that might be of recent relevance might be introducing cheetah in central India, right. Okay. Now we are asking is the stable equilibrium is an extinction equilibrium, those introduced animals will all go extinct. On the other hand, if it is stable equilibrium, they will keep on increasing, right. So, let us say is the extinction stable equilibrium or not. Now, I have introduced a few individuals for in this model. Remember that we are looking at logistic population model here, okay, with r greater than 0, and you look at the what is the population growth rate at this stage. So, the population growth rate when we have made a small introduction is actually positive. What does a positive growth rate mean? So, remember growth means increasing, right. So, positive growth rate, growth could be increasing or decreasing, right, but positive growth rate means things are increasing. So, for values close to 0, we actually have a positive growth rate in this model. So, therefore, we write an right arrow to indicate that the population size will increase further. Let us say the population size has gone here because it has increased further. Again the population growth rate is positive, it will increase further, and it will come here. Again you see that the population growth rate is positive, it will increase further. In fact, as the population increases throughout, the population growth rate is positive. So, population keeps on increasing until it hits or comes very close to the carrying capacity, right. And when I am reaching carrying capacity, the population growth rate is now getting back to 0. It is still positive, but it eventually hits 0 when you hit the carrying capacity. When you hit the growth rate 0, you are at an equilibrium, no changes happen. So, what this shows is that for a system that follows, for a population that follows logistic population growth model, the local extinction is an unstable equilibrium. It is unstable because when I introduced some individuals for an extinct population, that population kept on growing. Okay. So, we have now decided that therefore, this analysis shows us that n is equal to 0 is an unstable equilibrium. N is equal to 0 is an unstable equilibrium. Now, what about n is equal to k? Is it a stable equilibrium or is it an unstable equilibrium? To understand this, again now we will start looking close to this. I will use a different color now. Let us say I add a few individuals. As I say a system has now reached carrying capacity, I now introduce a few more individuals to this population and therefore increase the population to this level, a little above k. Now, at this point what is the growth rate? Okay, the growth rate is actually negative. So, look at this function has come down cross 0, it is now a negative value, it is a negative growth rate. So, therefore, when you have a negative growth rate, what happens? That means negative growth rate means the population actually is going to decrease. So, therefore, at this point the population will actually decrease and it will come here and it remains negative. So, it will decrease further, it will come here, the population growth rate remains negative, therefore, it will continue to decrease. It will continue to decrease up to the point it reaches the carrying capacity again. So, basically if a population has reached carrying capacity, if you add a few more individuals, they all basically die off and the system reaches back to the carrying capacity. Of course, the ones that you added may not die, anybody else in the population may also die, but the idea is that the overall population size reduces to reach back the carrying capacity. Okay. Now, this is a contrast to the density independent growth rate model, where the population kept on increasing exponentially because the resources were unlimited. Here we in fact we introduced the limiting resource concept by saying that the per capita growth rate is linearly declining with the population size. Okay. Now, we need to do one more little analysis to convince ourselves that carrying capacity is a stable equilibrium completely. Let us now delete a few individuals. I mean, let us say I kill a few individuals from a population which is at carrying capacity. What happens now? When you do that, the population size is reduced, but the growth rate is now positive. So, it will now increase, it will increase and come back all the way to carrying capacity. So, therefore, we actually denote the carrying capacity by a solid circle to indicate that if you make a perturbation on either side, it actually the population comes back to the equilibrium. On the other hand, we sort of denote unstable equilibrium 0 by a open circle to indicate that perturbation that we make actually moves away. Okay. So, to sort of summarize the aspect of equilibrium in the context of logistic model, for logistic population model is unstable, stable for r greater than 0. We have assumed that the parameter r is greater than 0. Okay. Okay. So, now having done this, let us now do a one final bit, which is to see if we were to plot n as a function of time, how would that look like. Okay. So, for the density independent case, it would just increase exponentially. However, for the case of logistic growth, it would look like this. Okay. So, this is the case of exponential growth, this is the case of logistic. Okay. So, I hope and in fact the logistic growth model curve looks similar to classic experimental curves that you do in a microbial biology lab, and the one that I also showed in the introductory class on population dynamics, where one of my colleagues took soil bacteria and soil microbes and grew in a laboratory culture. Okay. So, so this brings me to the end of this class. So, to summarize, we have learnt how to represent ecological population growth under fairly simplistic scenarios. The exponential growth corresponds to the scenario of density independent population growth, where the resources are not limiting, and the logistic growth corresponds to a simple case where there are limiting resources, and the ecological processes that lead to these limiting resources, for example, could be space, could be the amount of food, the intraspecific competition that leads to reduced per capita growth rate as a function of population size. Okay. Now, having these are the sort of two classic models of population growth. Okay. In the assignments we will I will give you some questions which are related to these and some extensions of these classic models, and in the subsequent lectures we will look at how do we write down equations when there are two interacting populations. Okay. And the two interacting populations can be in the context of competition for two species or predation between two species. Okay. With that note, thank you very much.